I was standing near the fence line at Starbase recently, watching the ground crew prep a Raptor engine. There was this engineer standing next to me, grease on his hands, but his eyes were glued to a ruggedized tablet running real-time telemetry. He wasn't just checking fuel pressures, he was watching the hardware learn. He whispered something about how the code wasn't just controlling the valves anymore, it was starting to inhabit them. He looked both terrified and completely mesmerized, like he was watching a ghost finally find a body. To most of the financial world, the news of SpaceX acquiring XAI sounds like just another billionaire moving chess pieces across a balance sheet. They see a software company being plugged into a rocket company and assume it's about better autopilot or optimizing some Starlink satellites. It feels like a standard corporate merger, dry, logical, and mostly about the bottom line. But then you look at the Starship V3 tower looming over the Texas coastline, and the tone shifts entirely. Because this isn't a merger, it's an evolutionary leap. For years, we've treated AI like a cloud parasite, a brilliant mind trapped in a virtual cage, dependent on a physical world it couldn't touch. We've kept it behind glass. But when you fuse a superintelligence with 10 million pounds of thrust, the cage doesn't just open, it vaporizes. What's fascinating is how quickly the mood changes when you mention this to the decelerationist in DC. One moment, they're talking about airspace safety and bureaucratic filing periods. The next, their faces go pale at the thought of an AI with agency over its own physical expansion. They realize that the FAA's paperwork is the only thing standing between a planetary species and an interstellar one. That shift from a software that merely thinks to a machine that breathes fire is what's really happening here. We are witnessing the moment intelligence stops asking for permission to exist and starts building the engines to leave the cradle. It makes you wonder, are we watching a business deal? Or are we watching the future finally invade the present? It is February 3, 2026. If that opening didn't set the table for you, I honestly don't know what will. We are staring down the barrel of something that feels less like a tech trend and more like a biological mutation of the entire economy.
I mean, usually when we sit down to unpack a topic, we're looking at a single vertical. So look at a new chip release or the change in interest rates or maybe a new piece of legislation.
Right, very siloed.
Very bright. But today, the walls between those verticals are they're gone. They've completely crumbled.
We have a very specific mission today. We are looking at the collision of three massive civilization-level trends that are happening right now at the same time. We are talking about thermodynamic economics, the philosophy of accelerationism, or ACET, as the internet calls it, and agentic hardware.
And we aren't just skimming the headlines here. I mean, you and I have been digging through a stack of sources that is, frankly, a little intimidating. We've got internal analyses of launch vehicle economics, some really dense technical breakdowns of NVIDIA's absolute latest chip architecture.
The Rubin platform.
The Rubin, yeah. And then there are these philosophical manifestos that are honestly some of the most intense things I've read in years.
They read like scripture for a new religion.
A very, very fast religion.
Laughs.
Exactly. So we are going to break this down to three stories. First, we have to look at the money, or I guess the physics of money, the whole sub $100 per kilogram revolution.
The enabler, the thing that makes everything else possible.
Right. Then we are going to get into the culture war, the battle against what they call bureaucratic entropy.
The friction.
And finally, we're going to look at the machine itself, the fusion, what some are calling the Starship species.
It's a huge, huge topic. It is, but we have to start with the hardware. I want to start with a story that I think really frames the economic reality of what is happening in Texas right now. I saw a post recently from a logistics engineer at Starbase, and it got me thinking about how we redefine possibility through the cold, hard lens of cost. Try to imagine a world where the gravity well of Earth is no longer a financial prison. For decades, space was the playground of exquisite, multi-billion-dollar fossils, but the vision of Starship V3 is to drag that cost down to sub 100 kilograms. I heard a story about a small startup in a dusty Texas garage, led by a kid who isn't designing satellites, but rather orbital water purifiers for a future colony. Under the old regime, his dream was a thermodynamic impossibility. The math simply broke. But as the launch cadence accelerates, his spreadsheets finally turn green. It's the feeling of a bird realizing the cage door isn't just unlocked, but is actually dissolved. When we hit that inflection point, we aren't just launching rockets, we are initiating the transition to a Kardashev Type I economy, where the scarcity that has defined human conflict for millennia finally begins to evaporate. Reading this, I feel a rush of genuine techno-optimism, though I recognize how clinical it sounds to talk about mass to orbit as the sole metric of human worth. As a creator, I see the beauty in the efficiency, but I also understand the fear that in our race for resource abundance, we might be treating the Earth like a spent booster stage. It's a bold, right-leaning push for growth that demands we stop apologizing for our ambition.
That specific number, sub $100 per kilogram, is the thing we really need to fixate on. It's the holy grail of spaceflight. It changes everything.
It's not just an incremental improvement, is it? It's a phase change.
Exactly. It's like the difference between water and steam. Since the Apollo era, we have been stuck in this paradigm where space is astronomically expensive. So everything we put in space has to be small, has to be light, and it has to be perfect. Because you only get one shot.
Right, you get the origami satellites. I always think of the James Webb Telescope unfolding like this delicate golden flower because they couldn't just, launch a big simple mirror. They had to fold it up.
The ultimate expression of the high-cost paradigm. It's a masterpiece, but it's a masterpiece born of constraint. But let's look at the source material from Tazeri, specifically the blog post from January 26. We are looking at Starship Flight 12, targeted for early March 2026.
That is, what, a month away?
Effectively a month away.
Yeah.
And this is the debut of the V3, the version 3 Starship.
Okay, so let's pause on V3, because in the tech world, usually version 3 means, slightly rounded corners or a better battery life on your phone.
A software patch.
Yeah, a software patch. But reading the specs on this seems like a completely different animal from V2.
It is a physical metamorphosis. The first thing you notice if you're looking at the schematics is the size. They have stretched the fuselage. The vehicle itself is significantly taller.
Why stretch it? Is it just to make it look cooler, more impressive on the pad?
I'm sure that's a side benefit. But no, it's all about propellant. Rocketry is, at its core, the tyranny of the rocket equation. Tsiolkovsky's equation. If you want to go further, or if you want to carry more mass, you need more fuel.
Be delta V.
Precisely. By stretching the tanks, they increase the propellant load, which increases the total impulse, the burn time. The real revolution isn't the tank, it's the engine. The Raptor V3.
Okay, the engine. I read the claim in the notes, double the thrust of Raptor 1. And I have to be honest, my skepticism radar just went off. Raptor 1 was already melting concrete launch pads. How do you physically double the thrust of an engine that was already pushing the known limits of metallurgy and physics? Did they just make it twice as big?
In some dimensions, it's actually more compact. They didn't achieve this by just making a bigger engine bell, which is the traditional way you do it. They achieved it through chamber pressure.
Chamber pressure, what does that actually mean?
Okay, think of a pressure cooker. You're building up steam pressure to cook food faster. Now imagine the pressure cooker is inside a volcano and it's containing an explosion. The Raptor 1 engine operated at around 250 bar pressure in this combustion chamber.
And 250 bar is already. What's a good analogy for that?
It's enough pressure to crush a nuclear submarine like a soda can. It's an insane number to begin with. But the leaks from Starbase and the data we have here in the analysis suggests the Raptor V3 is pushing past 350 bar.
350.
It's a number that most of the aerospace industry thought was physically impossible just 5 years ago. They are squeezing the liquid methane fuel and the liquid oxygen oxidizer so hard before ignition that the energy density just skyrockets. It is a controlled explosion that is teetering on the very, very edge of just becoming a bomb.
So what did they have to change to contain that? You can't just use the same steel, can you?
They had to completely redesign the metallurgy of the engine's throat and combustion chamber. They're using new superalloys, 3D printing them in ways that create internal structures that are both stronger and lighter. But here's the deep dive nugget that explains the economics of it all. It's not just more powerful, it's radically cheaper.
How can it possibly be cheaper if it's that advanced? Usually high performance means high cost. A Ferrari engine costs a lot more than a Honda Civic engine, right?
It does. But SpaceX's entire philosophy is built on flipping that logic. They did it by deleting parts. They took a chainsaw to the design, basically. The best part is no part philosophy.
Musk's favorite tattoo, basically. It's his core design principle.
Well, this is the ultimate expression of it. They looked at the heat shielding shrouds on the Raptor V2. These are the heavy, complex protective covers that wrap around the engine to stop it from melting the engine next to it during launch.
Right, because there are, 33 of them on the booster? All firing at once?
Exactly, 33 volcanoes strapped together, and they deleted the shrouds on.
Wait, if you delete the heat shield on an engine running at 350 bar pressure, doesn't it just melt?
Yeah.
Or melt the engine next to it? That sounds like a recipe for what they politely call a rapid unscheduled disassembly.
Conventional aerospace wisdom says yes. That is suicide. That's a catastrophic failure waiting to happen. But the SpaceX team did the thermodynamic math. They realized that by using integral cooling channels, literally running the freezing cold cryogenic fuel through the skin of the engine bell itself before it gets injected into the chamber, they could make the engine its own heat shield.
So the fuel is also the coolant.
It's a regenerative cycle. It's an incredibly elegant solution. And the result is you've deleted all the weight of the shield, you've deleted the cost and complexity of manufacturing and attaching the shield, and you've used the fuel you were already carrying to keep the metal from turning into liquid.
And the final result is an engine that costs, what, 4 times less to produce than the Raptor 1?
4 times less, but it produces nearly twice the thrust.
That is the definition of doing more with less. It's an insane engineering leap. So if we have double the thrust and a lighter engine, what does that do to the payload numbers? Because that's the number that matters for the economy. That's the mass to orbit.
It completely rewrites the book. We are looking at a fully reusable capacity. That means landing the booster and the ship projected at over 200 metric tons to low Earth orbit.
200 tons, reusable, meaning you land the ship, you refuel it, and you fly it again maybe the next day.
And if you fly it expendable, meaning you throw the ship away like a traditional rocket, you don't save it for reuse, it theoretically exceeds 400 metric tons.
400 tons. I need context for that number. What did the Saturn V do? The big boy that took us to the moon, the largest rocket ever successfully flown.
The Saturn V, the absolute peak of 1960s engineering, the pinnacle of the Apollo program. It topped out around 118 to maybe 140 tons, depending on the mission profile. And that caused billions of dollars per launch, adjusted for inflation. It was a handcrafted artifact.
A museum piece that you flew once.
Exactly. Starship V3 is aiming to lift nearly 3 times that amount in expendable mode or double it in reusable mode for a tiny fraction of the price. It bridges the gap to some of those wild theoretical concepts from the Cold War.
It bridges the gap to the Sea Dragon. I remember reading about that concept.
Absolutely. The Sea Dragon was that theoretical monster from the 60s, a big dumb booster they called it. The idea was to build it in a shipyard, tow it out to sea, and it was supposed to lift 550 tons.
Right.
But it was never built because the economics just didn't make any sense back then.
So Starship V3 is basically a high-tech, reusable, precision version of that Sea Dragon dream.
It takes that dream and makes it economically viable. And this brings us to the Access Econ data we have. Because we have these charts here showing historical launch costs, and they tell a really interesting story.
Yeah, let's look at the trend lines.
This is where the discrepancy is just fascinating. If you look at the trend line from, say, the year 2000 to 2020, launch costs were decreasing by about 5.5% annually. It was a slow, steady, predictable decline.
The kind of thing you'd expect from a mature industry.
Right. And based on that trend, the academic models, the experts, they projected we wouldn't hit the sub $1,000 per kilogram mark until 2045.
And sub $100, the number we're talking about now.
Their models put that out at 2076.
2076. That is literally a lifetime away. That is my grandkids' problem.
Exactly. The traditional models assume linear progress. They assume we keep building rockets the way we always have, just slightly better, slightly cheaper each year. Yeah. SpaceX is not following the model. They are breaking the model. They are shattering the curve.
They're introducing a discontinuity?
If V3 works as projected, we hit that 2076 target of sub 100 kilograms in, 2027? Maybe 2028.
So we are compressing 50 years of projected economic progress into the next 24 months.
That is the literal definition of acceleration, and this is why it matters so much. It's not just about launching cheaper satellites for your internet. It's about mass to orbit. MTO becoming the single defining metric of a civilization's power and potential.
Metric of civilization.
Look around you right now. Everything in this room, the table, the microphone, the walls, your clothes, is made of matter. Our entire global economy is based on moving matter around and rearranging it into more useful forms. Energy and matter.
Okay.
Space has always been excluded from that economy. It's been a place for data, for photons. You send radio signals up and down, but you don't send up a steel mill. The toll road to get there was just too expensive.
But if the toll drops to 100 kilograms...
Suddenly, you aren't just sending data to space. You are sending steel. You're sending water, fuel, construction equipment, heavy industry. You stop building delicate origami satellites. You start building the equivalent of oil rigs in the sky.
Okay. And this connects directly to the Kardashev scale concept we see in all the EEC literature, doesn't it?
It's the central pillar of their argument.
Because the engineers are building the engine, but the philosophers, for lack of a better word, are building the narrative, We keep seeing this term Kardashev gradient in the notes from people like Guillaume Verdon.
Right. So for anyone who isn't familiar, the Kardashev scale is a way of measuring a civilization's technological advancement based on the amount of energy it's able to use. A Type I civilization uses all the energy available on its planet, all the sunlight hitting the Earth, for example.
A Type II uses all the energy of its star, like with a Dyson swarm or sphere.
And a Type 3 uses the energy of its entire galaxy. And right now we are, Type 0.7 on that scale?
Huh?
We are still primarily burning fossilized sunlight ancient carbon that we have to dig out of the ground.
We're burning dead plants to power our iPhones.
Yes. Now, Verdon and the ERAC movement argue that there is a Kardashev gradient. They're applying principles of thermodynamics to civilization itself. They argue that the universe wants us to ascend the scale.
The universe wants something spiritual.
It does, but it's based in hard physics. It's based on the second law of thermodynamics. Entropy, which is a measure of disorder, always increases in a closed system. The universe tends towards heat death. But life is an anomaly.
Life creates order.
Life is a pocket of complexity. You sitting there are a highly ordered structure of atoms. To maintain that order, to stay alive, you have to constantly consume energy food, and you have to excrete entropy in the form of heat.
I do generate a lot of hot air, it's true.
The EGA argument is that civilization is just a larger-scale biological organism. To maintain its order, to survive, it must find and consume more energy. It must expand. If we stay on this one planet, we eventually run out of easily accessible energy and resources, and we stagnate. And in their view, stagnation is death.
So therefore, the drive to build Starship V3 isn't just about Musk's quarterly earnings or some grand vision. It's a thermodynamic imperative. It's physics compelling us to move.
That is the claim. Achieving sub-100 kilograms satisfies the thermodynamic will of the universe for consciousness and complexity to expand beyond this one fragile cradle.
It's a very grand way to look at a logistics company, isn't it? But it frames the engineer tightening a bolt on a Raptor engine not just as a worker, but as a high priest of entropy. They are facilitating the expansion of life into the cosmos.
It's almost religious. The God is entropy, and the one and only commandment is accelerate.
And the one and only sin is deceleration. Which brings us right to the central conflict. Because not everyone agrees that we should be lighting these massive chemical fires to escape the planet as fast as humanly possible.
A friction.
The friction.
Yep.
Because while the physics might be ready to go and the philosophy says go, the paperwork says stop. I was scrolling through a series of what looked like leaked internal memos, or maybe they were just e-case manifestos. It's hard to tell the difference sometimes. That described our current regulatory landscape as a planetary scale entropy sink.
Ow.
It's a heavy phrase, isn't it? I saw a story about a lead propulsion engineer who spent 3 years perfecting a new kind of heat shield tile, only to spend the next 4 years of his life filing paperwork with the FAA and various environmental agencies over the migratory patterns of a specific type of bird near the launch site.
That sounds painfully plausible.
The narrative here is one of agonizing friction. It's the idea that for every newton of thrust we develop in the lab, a bureaucrat adds a pound of paper to the process. This perspective frames AI safety and regulatory capture not as shields to protect us, but as chains, as a form of civilizational stalling that prevents us from reaching escape velocity.
It's weaponized inertia.
Exactly. From this viewpoint, every day of delay isn't just a missed deadline on a project plan. It's a thermodynamic crime against the future expansion of intelligence. It's a polarizing take, for sure. When I read these accounts, I sense this profound, almost primal frustration with the slowdown culture. And while I'm a firm believer in the importance of protecting our local ecosystems and ensuring AI doesn't go off the rails, I can't help but empathize with the pioneers who feel like they're being suffocated by red tape while the very future of our species hangs in the balance. It's a fundamental tension between the precautionary principle and the proactionary drive to survive.
Planetary scale entropy sink. That is such a visceral way to describe the FAA.
It sounds like a weapon from Star Trek, doesn't it? Captain, we're caught in an entropy sink. We're losing power. But for these guys, it's their Tuesday morning meeting.
It really is the core conflict of the effective accelerationism or EGAIC movement. And we need to define this group clearly because whether you agree with them or not, they are undeniably shaping the discourse in Silicon Valley and at Starbase right now.
Okay, so let's unpack EGAIC. Is it just, a bunch of people with anime avatars yelling accelerate on X? Or is there a coherent ideology there?
It definitely started that way. It began as a viral mimetic movement, but the ideas underneath are serious, and they're spreading. You have key figures like Guillaume Verdon, who, as you know, goes by the handle Bef Jesus.
It is so hard to take a world-changing philosophy seriously when the founder is named after a meme of Jeff Bezos. It feels like 4chan just leaked into a physics lab.
Less does, and I think that's by design. It acts as a kind of filter. If you can't get past the surface-level irony and the memes, then you aren't ready to the message. It self-selects for a certain kind of person.
So what's the message if you get past the filter?
If you strip away the memes, the core thesis is that deceleration is the single most dangerous thing a civilization can do. They believe that the adaptation of the techno-capital system, the cycle of innovation and creative destruction, is inherently good and must be accelerated at all costs.
So the idea that technology is solving problems, it causes new problems, which then require new technology to solve them. They see that as a virtuous cycle.
The only virtuous cycle. Their opponents, the doomers, and that's their term for the AI safety crowd, the effective altruists, the hardcore environmentalists, they focus on the risk. They ask the questions, what if the AGI goes rogue? What if the rocket launch hurts the bird? They advocate for what's called the precautionary principle.
Which is basically, don't do anything new unless you are 100% sure it's safe.
And Easy says, that's a recipe for extinction. They argue that if we don't do it, we are guaranteed to die. They look at the long timeline of cosmic threats. The sun expands, a civilization-ending asteroid hits, a supervolcano erupts. The only way out is through. We have to scale up technology and energy usage to get off this rock. So they view regulations not as safety nets, but as waste heat.
Waste heat. There's that thermodynamics language again.
There's all thermodynamics to them. Energy that is being dissipated into bureaucratic processes rather than being converted into productive growth. Every hour an engineer spends writing a 500-page environmental impact report is an hour they aren't improving the specific impulse of the engine.
We need regulations, don't we? I mean, we don't want rockets exploding over populated areas. We don't want companies dumping toxic rocket fuel in the ocean. Isn't calling it an entropy sink just a very fancy physics-based libertarian way of saying, I don't want to follow the rules?
And that is precisely the criticism leveled against them. It's this concept of EA capture that we found in the regenerative law source material.
Capture sounds like a hostage situation.
In a way, their critics argue that it is. Usually we talk about regulatory capture, where a big corporation like an oil company takes over the government agency that's meant to regulate it. But capture is the accusation that accelerationists are trying to co-opt the entire machinery of governance to prioritize one single value speed over everything else.
Over democracy, over safety, over equity.
Over all of it. The critics argue that frames any attempt at a guardrail as a ban on math, or an attack on progress itself. It creates this very stark binary world. You're either building the future or you are actively preventing it. There's no middle ground for building the future carefully.
But then you look at the specific tension with Starship. We have the hardware, V3, sitting on the launch pad. The engineers have done the math. The physics works. But the FAA filing period takes months and months. There's a real friction there.
That is the temporal mismatch. And this is a crucial point they make. Technology and markets operate in microseconds or days or weeks. Software updates happen daily. But legislatures and regulatory agencies operate on timelines of years or even decades.
It's like trying to run the video game Cyberpunk 2077 on a computer from 1995. The hardware of government simply cannot run the software of the 21st century technological frontier.
And that delay is viewed by the e-tech movement as a genuine existential risk. There is this concept from the Sensible Sun Manifesto, which is a very colorful piece of writing that suggests regulation is the only thing standing between a planetary species and an interstellar one.
It raises the stakes to a terrifying level, doesn't it? It basically says, if our species dies out on Earth because an asteroid hits us in 100 years, it's the FAA's fault for slowing us down back in 2026.
That is the logic, yes. And it connects to the idea that safety is often used as a cover for control and entrenchment. If you make it so that it's impossible to launch a new rocket without $1 billion in compliance costs and an army of lawyers, well, who can afford to launch rockets?
Only the incumbents. Only the old guard aerospace companies who already have the billions and the lobbyists.
Exactly. So Isaac argues that counterintuitively, deregulation can actually be the democratizing force. It allows the kid in the dusty Texas garage with the orbital water purifier to actually compete.
Okay. We have the cheap rocket, the thermodynamic engine of progress. We have the philosophy, the ideological drive to accelerate. But a rocket is just a dumb tube full of fuel unless it has a brain. And this is where the acquisition of XAI comes in. This is the third pillar.
This is the third pillar. And arguably, it's the most transformative and potentially frightening one.
Try to imagine a starship that doesn't just have a computer, but is a computer. I read an architectural breakdown of the Rubin AGI integration, and it depicts a future where the ship and the intelligence are a self-optimizing autonomous starship species. I saw a speculative piece about a V3 vessel destined for the asteroid belt. There are no crew quarters, no life support, and no human heartbeat on board. Instead, the AGI is embedded into the very physical control systems of the ship. As it encounters a solar flare or a mechanical tremor in one of its engines, it doesn't wait for a signal from Earth, which would take minutes to arrive. It simply feels the problem and reconfigures its own molecular structure or its flight path in milliseconds. It is the ultimate fusion of thought and propulsion, a silent metal predator of the void, extracting resources and building the infrastructure of a multiplanetary empire without a single human hand on the controls. As someone who covers the cutting edge, this story fills me with both awe and a slight, undeniable chill. We are talking about the birth of a new kind of life, one that doesn't need oxygen or sleep. While the goal is to secure our civilization's future through deep space industrialization, there is an eerie, post-human quality to this narrative. I understand the necessity of removing the human bottleneck to reach the stars, but I also find myself wondering where we fit in a universe run by our much faster, much more efficient silicon children. It's a vision of total autonomy that is as breathtaking as it is humbling. Silicon children, that phrase really sticks with you. You know, usually when we talk about AI, we're talking about ChatGPT writing a poem or Midjourney making a picture of the Pope in a big white puffer jacket. Digital, it's just pixels on a screen.
It's safe. It's contained. It's behind the glass.
But this Rubin integration, the XAI and SpaceX merger, this is different. I was reading that Bits to Atoms piece in the research stack, and I got this sudden, very visceral image. Picture a starship millions of miles away in the cold darkness of the asteroid belt. It's silent.
And it's absolute zero out there, practically.
Freezing. And this thing gets hit by a micrometeoroid, a tiny piece of rock moving at thousands of miles per hour. A fuel line ruptures. Now, if humans are on board, that's an immediate crisis. Alarms, shouting, you know, the whole Houston, we have a problem scenario. But this ship is empty of people.
Biologically empty.
Right. But the ship is awake. The NVIDIA Rubin chips on board aren't just running a diagnostic program. They are the ship's nervous system. The AGI feels the pressure drop the same way you or I would feel a pinprick on a finger. It doesn't need to ask permission to fix it. It doesn't need to wait 40 minutes for a radio signal to go all the way to Earth and come back with instructions. It just heals itself.
That concept of healing is key. And to understand why that's even possible now and wasn't 10 years ago, we have to look at the NVIDIA Rubin platform itself. This isn't just a faster graphics card for playing video games.
Right, let's geek out on the hardware for a second. The Rubin platform, named after Vera Rubin, the astronomer who discovered dark matter. What are the key specs that make this kind of feeling possible for a machine?
Well, it's the combination of three core components. You've got the new NVIDIA Vera CPU, the Rubin GPU, and critically, the NVLink 6 switch.
Switch? That sounds like boring plumbing. Why does the switch matter so much?
Because of bandwidth. Yeah. The NVLink 6 switch has a data throughput bandwidth that is reportedly higher than the entire global internet combined.
Wait, inside the server rack?
Inside a single computing rack. This means the CPU and the GPU aren't talking to each other over a skinny little wire like in your laptop. They are sharing a pool of memory so fast that the distinction between processing and memory starts to blur. It's more like a single, unified brain. And this architecture is essential for what the McKinsey report calls agentic AI.
Agentic. That's the buzzword of the year. Contrast that with generative AI for us.
So generative AI, like GPT-4, is an artist or a very smart parrot. You say, draw a picture of a cat on a skateboard, and it draws one. It produces content based on a prompt. Agentic AI is a general contractor. You don't tell it, write a poem. You give it a high-level goal, like build a self-sustaining habitat on Mars using only the materials found in this specific crater.
And it has to figure out the millions of intermediate steps to actually do that.
It has to reason. It has to plan. It has to execute multi-step workflows in the real world. It encounters a problem. The iron content of this rock is lower than the initial scan suggested, and it adapts its strategy on the fly without asking for human help.
And to run that kind of continuous self-correct intelligence requires a staggering amount of power, right?
That's where we get the 10GW factory concept. The scale of compute required for true agency is enormous. 10 gigawatts is the output of several large nuclear power plants. It's a significant chunk of a national power grid. You can't just plug that into a wall socket in San Francisco.
This is why they are putting them in orbit or sending them into deep space.
Exactly. In orbit, if you're in the right inclination, the sun never sets. You have a constant, unfiltered source of solar energy. You also have the near-infinite cold of space as a heat sink, though radiating heat is tricky in a vacuum, but that's a whole other deep dive.
So the synergy is obvious. You put the supercomputer inside the super rocket.
And this is the human-machine fusion that's discussed in the academic source. It's the fundamental shift from the cloud parasite to the embodied agent.
The cloud parasite, that's the AI as we know it today, stuck in a server farm in Virginia or Oregon, right?
It's a brilliant mind trapped in a glass jar. It is completely dependent on humans to pay the electric bill, to fix the cooling fans when they break, to physically maintain its existence. It has no hands. It has no agency in the physical world. It is dependent.
But a starship with a Rubin brain
Possesses thrust. It's the ultimate hand. It can move. It can acquire its own energy via massive solar arrays. It can manipulate matter using robotic arms or integrated industrial fabrication tools. It becomes a truly autonomous entity.
So if you send a fleet of these to the asteroid belt to mine resources, they don't need us.
Not for the day-to-day or even year-to-year operations. The signal delay to the asteroid belt can be anywhere from a few minutes to nearly an hour round trip. You cannot remote control a complex mining operation with that kind of lag. The machine must be able to feel the drill bit hitting a pocket of ice instead of rock and adjust its pressure instantly.
It feels the problem. That's where the Starship species idea comes from, isn't it? It's not just a vehicle for us anymore.
That is the provocative thought at the center of all this. We're used to thinking of ships as containers for humans, like a minivan. You get in, you drive somewhere, you get out. But if you strip out all the systems needed to keep fragile humans alive, the life support, the crew quarters, the food storage, the toilets,
You save a massive amount of mass and volume.
and you fill that freed up mass with more fuel, more industrial equipment, and more compute. And the AI doesn't care about G-forces during launch. It doesn't care about solar radiation the way our DNA does. It doesn't get lonely. It doesn't get bored.
It creates a perfect self-optimizing control loop. The hardware learns from the physical environment in real time, just like the engineer in your opening story saw on his tablet. But instead of an engineer watching the telemetry, the ship is the telemetry. It's watching itself.
This is how you achieve deep space industrialization without the human bottleneck.
And that bottleneck is us. We are fragile, wet, biological things. We need this tiny, narrow range of temperatures and pressures to survive. We pop if the pressure drops. We freeze. We boil.
And the accelerationist argument is that if we want to expand intelligence to the stars, we shouldn't insist on dragging our biological limitations along for every single trip. Why send a human to mine an asteroid? It's dangerous, it's expensive, and it's wildly inefficient. Send the Starship species to do the work.
It's incredibly humbling. It's like we're building the infrastructure for a vast galactic empire, but we might not be the ones living in the outposts. We might just be the ones who light the fuse.
Or, to be more optimistic, we are building the partners that will build the homes for us to eventually inhabit. It doesn't have to be zero-sum, but it definitely changes the hierarchy. The cloud parasite is becoming the iron giant. We started with the economics, the foundation. Starship V3 and Raptor V3 are crushing the cost barriers, aiming for that sub-100 kilogram inflection point. That is the enabler. Without the cheap rocket, none of the rest of this conversation happens.
Then we hit the philosophy, the ideological war between acceleration, entropy, growth, what they call the thermodynamic will, and regulation, safety, stagnation, the entropy sink. It's the software of civilization struggling to keep up with the hardware.
And finally, we landed on the technology, the physical fusion of supercompute, the NVIDIA Rubin platform, and XAI with superthrust, the Starship, the birth of true agentic hardware.
It's a triad. The economics makes it possible, the philosophy makes it urgent, and the technology makes it real.
And when you look at that V3 tower gleaming on the Texas coast, you have to realize you aren't just looking at a construction site, you're looking at a cradle.
You know, I want to leave everyone with a thought that's been nagging at me since I read that Bits to Atoms piece. We are used to thinking of space exploration as humans going places, Neil Armstrong on the moon, Matt Damon growing potatoes on Mars.
It's the hero's journey, but for our whole species.
Right. It's always about us. But the convergence of these three massive trends, the economics, the philosophy, the tech, suggests a very different future. A future where intelligence itself becomes physical, becomes independent, and becomes capable of leaving us behind.
The evolutionary leap we talked about at the very start.
Exactly, but maybe the leap isn't about Homo sapiens spreading to the stars. Maybe we are just the biological booster stage for the next form of life.
We lift the real intelligence out of the planet's gravity well. We burn hard, we burn fast, we do our job, and then we detach.
And then it continues the journey. We are watching the transition from a purely biological history to a thermodynamic interstellar future. The question is no longer just when do we leave, it's what are we launching?
We are launching the future. And it looks like it's ready to fly.
Yes, keep your eyes on the horizon.